Ladies and gentlemen, welcome to our webinar on the UltraCam Dragon 4.1. The speakers of today are Marc Muick, Head of Applied Photogrammetry for Camera and Calibration, Bernhard Schachinger, Head of Applied Photogrammetry for Data and Workflow, and Alexander Wiechert, myself, CEO of Vexcel Imaging. If you have questions during the webinar, please type them into the Q&A pane and we are looking forward to answer them at the end of the webinar. The webinar will be recorded and we will share it later. The UltraCam Dragon 4.1 is our first hybrid aerial mapping system from our integrated line. It collects nadir and oblique imagery and LiDAR integrated in one system. Many of you asked the question, why did we design the Dragon now and not earlier or later? The answer is easy, because the time was just right for it. Technology evolved in a way which enabled us to overcome with the shortcomings of integrated sensors we have seen in the market so far. They typically suffer from inhomogeneous LiDAR scan pattern, overemphasizing the edge of the strip, no dedicated nadir LiDAR scan line, a mismatch between image ground sample distance and LiDAR point density, a mismatch of the mission parameter, so the result was always a bad compromise which leads to not so great flying efficiency and not so great data quality. The development of the new RIEGL VQ680 OEM changed the game. In combination with the UltraCam nadir and oblique camera cones, the missions parameters now match, image ground sample distance and LiDAR point density fits together. True nadir and oblique LiDAR scan lines obtain best-in-class LiDAR coverage, and as a result the flying efficiency is where we wanted it to be and the data quality sets the industry standard in imagery and LiDAR data. That is why the Dragon is out now, to get you the best hybrid sensor available on the market. With the UltraCam Dragon 4.1 you can expand into new applications like 3D city modeling, forestry, disaster management, precision agriculture, corridor mapping or hydraulic simulations. Now showing just a few eye candy imagery on how this would look like. So that's an example how you can use your Dragon to obtain 3D city models in a very efficient, precise and super quality. Or you can use it for power line monitoring. And please have a look on these on the quality of the LiDAR point cloud you see on the fine linear structures. Isn't that impressive? Or you can fly it for change detection, monitoring what's going on over time. Or precision agriculture, you're monitoring your crops. The UltraCam Dragon 4.1 consists of three subsystems. It has the camera, it has the LiDAR sensor, and it has integrated our UltraNav version 7 610 GPS, FMS and INS system for the mission guidance. The engineers were capable in squeezing everything into the housing of our fourth camera generation. That means power consumption is in the range of the fourth generation, the weight is very efficient, and also the cylinder diameter fits to existing environments like the Ultra mounts. The UltraCam Dragon comes with several peripherals. So first of all, it has three screens to monitor the system, the LiDAR, the imagery, the flight mission. Then it has data units, solid state drive data units, 16 terabytes, 32 terabytes, very high in volume, very small in form factor. It comes with a transfer unit which is required to download the data into the processing system. And then it has the Ultra mounts. And newly developed, we have our unit lifter. This unit lifter is to enable you to move the system up and down. So you have it up during takeoff and landing to protect the system. And you can lower it during the mission to obtain a clear field of view for the cameras and for the LiDAR. That unit lifter Pro 72 has three lifting heights, up, middle and down, to address several installation scenarios. It is compatible with all fourth generation UltraCams and all Ultra mount systems. It's super user-friendly to install. You can do it in 15 minutes or so, and it allows you a very smooth and effortless operation because it has gas springs supporting the lift of the system. With that, I am handing over to Marc Muick, Head of Applied Photogrammetry for Camera and Calibration. Marc will talk more about the camera and the LiDAR subsystem of the Dragon. Marc, the floor is yours.
The camera system is composed of 4 150 megapixel RGB oblique cones, one 150 megapixel nadir RGB cone and one 150 megapixel nadir near-infrared cone. All of them are utilizing our well-proven 3.76 micron CMOS sensor. In order to make room for the LiDAR, the oblique cones are arranged around the LiDAR and therefore necessitate the usage of the also newly developed Unit Lifter Pro. The Dragon is available with two different focal length options. The first option is the f80 version, equipped with 80mm nadir lenses and 123mm oblique lenses. Option 2 is using the 50mm lenses in the nadir and the 80mm lenses in the oblique cones. Our camera designs always aim to create the utmost collection efficiency. Therefore, the oblique cones are oriented in a way that the longer side of the image sensor always faces in flight direction. Furthermore, we are also slightly shifting our left and right oblique cones to collect more details closer to the airplane because of its higher ground sampling distance. This is possible due to the large image circle of our custom designed lenses, which are delivering stellar performance even towards the edge of the image circle. The next key feature in the mighty arsenal of the UltraCam Dragon 4.1 is our industry-leading software-based multi-directional motion compensation approach called the adaptive motion compensation. The adaptive motion compensation is the only solution that can correct for multi-directional blur, so translational and rotational blur, considers image scale variations in oblique imagery, handles scene-specific motion blur variations, and eliminates crucial mechanical parts of the camera. I'm really excited to show you some, from my point of view, very powerful and speaking examples of how the adaptive motion compensation is the game changer for consistent image quality. We have two images captured at 2.5 centimeters directly one after the other. The first image has a combined motion blur, so translation plus rotation, of 5.62 pixels versus 2.36 pixels on the second image. The quality level difference between the two images shown at the 200% zoom level is quite obvious. Now check out this significant difference when AMC has compensated the image blur of both images to 0. The second example features some fine structures on a parking lot. On the left image, the fine structure is basically gone and not visible any longer, while on the right image some details are visible, but certainly not on the quality level that Vexcel is known for. After AMC has done its magic, consistent image quality is achieved for both motion blur scenarios. AMC significantly reduces your project risk. With AMC, you will always produce sharp imagery, finish your AI faster, make any ATC window count, take advantage of smaller weather windows, and gain capacity for additional work. For some final impressions of the camera part of the UltraCam Dragon 4.1, I want to show you some amazing imagery that was collected over Mehsana in India. So, camera done, LiDAR is next. The UltraCam Dragon 4.1 features the RIEGL VQ680 OEM LiDAR scanner. Being a Class 3B laser product, it is not eye safe for users at close range. In an aerial application, it is still necessary to comply with either the nominal ocular hazard distance or the extended nominal ocular hazard distance. The VQ680 offers online waveform processing, multi-target capability, and operates in the near-infrared spectrum of the light. Positioned more or less in the center of the UltraCam Dragon, the VQ680 is based on a rotating polygon mirror. It furthermore features a laser pulse repetition rate of up to 2.4 MHz, scan rates of up to 500 lines per second, can conduct up to 2 million measurements per second, and resolves a maximum of 32 targets per pulse. The most unique feature of the VQ680 is its scan pattern. The rotating polygon mirror has 5 individual facets, which create 5 linear scan lines at differing viewing directions. Those are composed of a pure nadir view, one view at plus 10 degrees, one view at minus 10 degrees, one view at plus 20 degrees, and one view at minus 20 degrees. Having 5 different directions combined with a very big opening angle of 60 degrees, the UltraCam Dragon sets new standards in terms of efficiency and quality alike. In order to get a better idea of the benefits of this innovative scan pattern, it makes sense to compare it with other LiDAR scan principles like a circular scan pattern. Let's dive in a little bit deeper into how the innovative scan pattern of the UltraCam Dragon benefits your projects from a quality perspective. Benefit 1. The true nadir view enables the collection of urban canyons and will even capture 3D points in the narrowest streets. Benefit 2. The 5 viewing directions are maximizing your point density in the vertical. This is especially advantageous in urban environments where vertical objects like facades can be more accurately identified. Furthermore, this approach also optimizes vegetation penetration to its highest potential. Ultimately, this leads to capturing the maximum number of last echo, thereby facilitating the creation of a precise terrain model. Benefit 3. One of the major benefits of a linear scan line is the uniform point distribution across the flight strip. LiDAR scanners built around a rotating wedge design have the capability to not only create circular scan patterns but also elliptical ones. Nevertheless, when using a circular or elliptical scanning system for mapping, the laser scanner spends more time collecting data at the edges than in the center of the flight line as the plane moves forward. This means it scans the same area at the edges many times, which does not improve accuracy but creates extra data that is not needed. So with the UltraCam Dragon 4.1 you get a more balanced sampling across the flight strip. We are starting with a simple plot where the horizontal axis is displaying the flight line width in meter and the vertical axis is displaying the point density per single flight strip per square meter. The cyan color is associated with the linear scan pattern as used in the UltraCam Dragon 4.1, and the magenta color represents the results of a circular scan pattern. Let's start with a plot of the average point density. By only utilizing this metric, it would seem as if the circular scan pattern is superior, but only at a first glance. Let's now bring in the real point densities across the flight line. The linear scan results in a marginally different point distribution across the flight strip with a maximum in the center of the line and very shallow decline towards the edges. The circular pattern, on the other hand, creates a totally different distribution with very different point densities in the center versus on the edges. This bathtub shape is typical for this kind of measurement principle, and it comes with a number of drawbacks. The most obvious one is the very high number of points on the edge that are not really meaningful for the user. In order to deal with this problem, filtering is needed to reduce the point density of the corner regions to the point density of the center. So for the largest part of the flight line, the linear scan pattern is actually superior. So to recap, linear scan patterns create a more uniform point distribution, are not prone to excessive oversampling at the edges, and do not undersample at the critical center. I hope I have offered some valuable insights into the UltraCam Dragon 4.1's LiDAR system and the camera system. Now my trusty colleague Bernhard will take over and show you some collection scenarios.
Thank you, Marc. I'm going to talk now about various scenarios where the data can be used and the scan pattern brings benefit. So, as you have heard earlier, we have scan lines that capture data at 5 different angles. That allows full coverage of features from all sides. There are almost no occlusions due to the true nadir scan, and there is a very even distribution of points in the swath. Finally, all that allows to focus on efficient planning based on the swath and not on a point pattern. I would like to show you an example from a flight with 5 cm GSD in the nadir image, which results in a point density of about 26 points per square meter. The example is from a narrow alley in Graz, which has a width of about 1.5 meter, and the height of the buildings next to this alley is about 13 meter. So here first an example of the point cloud, which is captured with the view of plus 10 degrees. We see a 3D view of that point cloud area, then we see a top-down view, and on the right hand side there is a cross-section through this point cloud. There are points visible on the roof, of course, then on the facades, and even a few single points down on the ground. But there are a lot of areas where there are no points. Now the same scene with the viewing direction minus 10 degrees. Here we do have coverage with points in other areas. Now the same with plus 20 degrees, where there is coverage again with some other points in other areas. Finally now minus 20 degrees, adding more points and combining all of these then to a view including nadir, we see now that there is full coverage on the facades and on the ground. So the green points here, these are the nadir points, which clearly bring benefit to about half of the width of the alley on the ground. Besides the scan pattern, the Dragon supports with various operation modes the great variety of use cases and scenarios. So of course we do support the hybrid data collection, where nadir images, oblique images and the LiDAR point cloud are captured at the same time. Then there is a camera-only operation mode where nadir images and oblique images are captured. And oblique images could be deactivated if not needed. And finally, there's the LiDAR-only operation, which allows to capture the point cloud but do not capture any images. All these operation modes allow to save processing time and storage space. For our UltraCams that support oblique image capture, like the Osprey and the Dragon, we offer various oblique image modes to be able to react to various needs of use cases. So first, there is the standard operation mode, where the nadir image and all 4 obliques are being captured. So that is useful, for example, for city modeling, where you need full coverage from all sides. Then we do offer a mode for corridor mapping, where the sideward-looking oblique images are being deactivated, and just the nadir image and forward and backward-looking oblique images are being captured. For the Dragon, in this mode, of course, data capture with LiDAR is also possible. So then nadir, forward, backward and LiDAR data is captured at the same time. And finally, there's the nadir-only operation mode, where all 4 obliques are switched off, just the nadir image is being captured. There are 2 ways how to use these modes. So either for the data collection, the camera cones can be deactivated, so that only these cones that should record data are actually recording. And then on the other hand, if the recording of the data has been done with all camera cones, then in the post-processing step in UltraMap Raw Data Center, the data that should be processed can be selected. And in that way, then storage space while processing and also processing power, so processing time, can be saved. Taking advantage of the scan pattern and the oblique image modes, we can talk about various scenarios which might be typical for the use of the Dragon. So first there is ortho mapping, where the goal is to produce an ortho mosaic, either based on the DSM or on the DTM, and maybe also producing stereo pairs. The flight plan in this case is driven by image parameters and also considerations for the ortho product, like the building lane. A typical overlap in flight direction could be 80%, and the sideward overlap could be in the range of 30 to 60%, depending on the terrain and the project requirements. In the case of the ortho production, the capture and processing of oblique images can be switched off if they are not needed, so therefore storage space and processing time can be saved. Depending on the requirements for the ortho mosaic, the image overlap across might be low, because the LiDAR offers a much bigger swath than the image and allows therefore a robust creation of the DSM and the DTM, so dense image matching not absolutely required in this case. And also the image GSD of about 5 cm results in 26 points per square meter for one flight line, which is easily enough for a DSM and DTM creation from LiDAR data. So sideward overlap of line adds to a point density of up to more than 100 points per square meter in case of 60% overlap across. So therefore, depending on project needs, sideward overlap could be reduced significantly to save cost and flying time. The next scenario is corridor mapping. The goal is to produce image coverage with the nadir and oblique images, and also some derived products, and also to capture a point cloud. So all that data that's maybe needed to capture a power line and describe the characteristics of the object itself and also the nearby surroundings. A flight plan could be like 80% in forward direction or even more. And if it's just one single power line, then there is likely no sideward overlap needed. So in that case, the sideward looking obliques can be switched off so they are not captured by the camera and save storage space. The GSD for such a corridor mapping project might be driven by the image component on the one hand, so that the images show visible features and details on towers of the power line, for example. And the GSD might also be driven by the LiDAR component to capture geometric features like cables or rails. Example GSDs for such projects could be first 2 centimeters. 2 centimeters in the nadir image are captured from 426 meters above ground level, and that results in 65 points per square meter for one single flight line. And then an alternative GSD could be 2.5 centimeter captured from 532 meters above ground, resulting in 52 points per square meter, also again for one single flight line. Both of these are captured with the 80mm lens of the Dragon. Another scenario is city modeling, where the goal is to capture nadir and oblique images and the point cloud to be able to create products ranging from stereo pairs over the DSM, DTM, orthomosaic to a 3D surface with textures. And also vectorized models like bindling models and tree models can be derived from such data. The flight plan is driven by the reduction of occlusions. The flight plan for such scenario is typically 80% in forward direction and typically sideward 60% or even more. As we have seen in the example of the narrow alley earlier, the LiDAR scan pattern supports data collection in most challenging local situations. Let's talk about the workflow for processing data of the UltraCam Dragon. So we are using purpose-built software products that can be combined as needed for a project. The big advantage is that the software products are well proven since many years and benefit from the rich expertise of the development teams of the vendors. Another benefit is that the processing tools are the same for data from the Dragon, as well as for single cameras or LiDAR sensors. So there is no additional effort for training staff when working with data from the Dragon. And we have experience with a lot of processing tools and can assist with creating the best workflow for a use case. Our close ties with many software vendors help to ensure a smooth integration. Here's an overview of the software workflow from planning to basic processing of a project. So first there's the planning step with top-of-flight and RIEGL software. Then there is the data collection, and finally there's the processing of the data, where on the one hand camera data is being processed in UltraMap, navigation data is processed with UltraNav components in Applied Photogrammetry, and LiDAR data is being processed in the RIEGL software RiPROCESS. So let's have a quick look at UltraMap. UltraMap is our software for processing raw data of the UltraCams. The data that is captured by the cameras can be imported in the software, and then a project can be created. And then based on this project, based on the image block, we can do error triangulation, radiometric adjustment of the images, dense image matching, deriving a DTM, creating orthomosaics, and finally creating a 3D mesh from nadir and oblique images. For the LiDAR side, there's RIEGL LiDAR. This software can also handle the raw data that is captured by the sensor and then do some post-processing of this raw data, then doing georeferencing of the data, bringing in ground control, doing an additional filtering step of the data, and finally exporting the data to formats like LAS. So the big question for the Dragon is how to bring both data sets together, so to well align the images that come from UltraMap and the point cloud data that comes from RIEGL LiDAR. The alignment of these datasets can be done with some features that are measured in both datasets. Measurement of features is in images much easier than in the point cloud. UltraMap provides an easy way to collect high objects, which can be used then in RiPROCESS. Roof planes, for example, can be easily captured in image data by measuring the corners of the roofs, and then these roof planes are being imported in RiPROCESS, automatically detected there, and used for translation and correction of the block. The results of the workflows with UltraMap and RiPROCESS are for most use cases just some intermediate results. So most likely use cases will require that there is some third-party software involved to respond to any scenarios that are needed. For example, first there might be a need to create a vectorized 3D city model. That could be done either from imagery and or the LiDAR point cloud. One approach is to use the images and do extraction of features in a stereo environment with a semi-automated approach, like shown here. There is first some creation of a model with geometry, so vectors, and then these vectors, these building models, are then textured with the image data with nadir and obliques. Another example for generating vectorized 3D city models is a workflow to use automatically generated building models. So such a workflow might use available vector data from external sources such as building footprints or cadastral areas. And then these could be used to split areas to create building models and first create geometry and then texture these models. Another use case is to create colorized LiDAR point clouds. So per default, the point clouds from the Dragon are not colorized. So the points, they are just XYZ coordinates. But a third-party software allows to bring RGB and near-infrared values to the LiDAR points. That would allow, for example, the calculation of index values like the NDVI or the water index directly on the point cloud, just next to nice visualizations with RGB of the points. And finally, a 3D mesh can be created from a combined processing of imagery and LiDAR data. So that then brings together the benefits of images and LiDAR both into one product to be able to have most precise geometry for the mesh 3D surface. That can be done with a fully automated generation of the data. So with that, I would like to hand over back to Alexander. Thank you.
Thank you very much, Bernhard, for this excellent presentation. Ladies and gentlemen, we are now coming towards the end of our webinar and we are opening up the Q&A session. So if you have questions, please type your questions into the Q&A pane of the conferencing software and we are looking forward to answering your questions. Hello everybody, I hope you enjoyed the webinar so far. So we are now opening up the Q&A session. So I jump into the first question. Thank you for this great presentation. One main question, can the UC Dragon be used on pressurized plane with windows on the floor? The nadir line of the RIEGL 680 could damage the reception state to the direct deflection on the window inside the plane. So that's totally right. And we are currently investigating solutions together with RIEGL, which so that the Dragon could be installed in planes with a pressurized glass. So I can't say yes or no at this point in time, as we are technically investigating the situation. Having said this, a glass is never helpful for quality. It's not helpful for the camera and it's not helpful for the LiDAR. So if possible, sensors should be operated without any glass, but I understand that there are planes which have glass installed and you don't want to remove it. And that's why we are currently investigating a technical solution to make the Dragon work also for this scenario. Next question is, if I'm interested in testing the Dragon on a small test site, would there be any options to do so? Any systems for rent short term? So we are definitely open to run demos on the system, as we understand that this is something new and people want to get a first-hand experience on it. So when you are interested in doing so, please be so kind and contact us. If you already know, contact your sales rep or ping us through our other channels, and we are happy to work with you on the case to demo a Dragon. Thanks for the webinar and all information. As far as I know, LiDAR point cloud doesn't use ground control points for bundle adjustment, where oblique cameras use ground control points which serve better accuracy. How does LiDAR point cloud exactly fit to the photogrammetry output? So that's the first question. How does LiDAR point cloud exactly fit to the photogrammetry output? And the next question is UltraNav 610 good enough for that? And that's a question I would like to hand over to Bernhard, please.
Yeah, very good question. So I would say there is not a single general answer to that, but it depends a lot on the use case and on the requirements of the project. So there might be projects where direct georeferencing is fine and the LiDAR can rely on the trajectory. There might be other cases where there is a requirement for best alignment of image data and LiDAR. So that means some tie objects make sense to be used to reference both data sets to common features. So yeah, it fully depends on the needs of the project.
Yeah. And the general answer would be 610 accuracy leads to a very good georeferencing of the imagery and the LiDAR point cloud. And of course, the system is calibrated, so they are adjusted to each other. But with the workflow, how you described, one can improve the absolute accuracy.
Right, yeah.
Good. Okay. A question here is, what is the imagery frame collection rate? so the collection rate can be adjusted according to the project needs, and the fastest possible frame rate is 0.7 seconds between two frames. So the camera shoots a frame in every 0.7 seconds. Pretty fast. So that enables to fly low and fast with a high forward overlap. And that frame rate is common across the fourth camera generation of UltraCam. So also RIEGL has the 0.2 or Condor and so on. Next question here is, I'm interested in adaptive motion compensation. Do you also compensate for blur in the obliques or just nadir? So the compensation is done in all imagery, nadir and oblique, compensating oblique is a huge advantage, because the oblique images suffer pretty much from a change of scale as they are looking oblique into the scene. So the change of scale between the pixels close to the ground and the pixels higher up in the air is massive. And motion compensation and adaptive motion compensation addresses this. But also when the plane has some roll angles involved in while flying, the movement spoken in pixels in the oblique imagery is massive. And so the adaptive motion compensation plays an especially important role in the oblique imagery, as we see significant motion blur and very inhomogeneous motion blur and significant change of scale. And all these aspects are addressed by the adaptive motion compensation, while all the other procedures fail on this. What will be the range of point density with fly heights for GSD of 20 centimeter? Am I right if I say the point density is 0 because it's out of the range of the LiDAR?
Yes, that is true. So the construction principle or the design idea of the Dragon is around the GSD idea of, let's say, a 5 to 10 centimeter range for urban mapping. So this is what the general idea of that sensor and its application is. So also if we take use cases like Bernhard showed us before in terms of corridor mapping, power lines, anything like that is perfectly fitting into these GSD categories.
Yeah. So the design principle of the Dragon was high resolution. It was not to cover wide areas in LiDAR and imagery. For this one could install, for example, an Eagle and a RIEGL 1560, which could then go up really high into the air and have a massive collection efficiency. I'd like to have a look on the data. Where can I get the samples? Bernhard, please.
Yeah, so we are very happy to provide sample data. If you're interested, please reach out to us or reach out to the sales guys in your region, and then you will be provided with credentials.
Next question is again an adaptive motion compensation. Does AMC get images with a value of 7 to 9 or higher down to 0 as well? And I'm assuming with 7 or 9 here, that is meant the blur in pixels, because the demo showed images with values at 2 to 5. Yeah. So what's our experience here, Marc, Bernhard, with pixel motion blur in the range of 7 to 9?
So I think I can take that one. Since the AMC has been around since the Osprey 4.1, we have a pretty good knowledge of what works and what doesn't, and also what we can compensate or what the quality of that compensation is. Values of up to, I would say, 10 to 11 pixels is something that we can compensate quite nicely. But this should not be basically the aim or what we are aiming for. So the whole exposure strategy of the Dragon, and the same is true here for the Osprey, is built around the idea that we are trying to stick to a motion blur as a, let's say, a standard forward motion of, let's say, 2 to 3 pixels or less than that. When you have that kind of forward motion, when you're flying is a very dynamic thing. You will get gusts, you will hit bumps, you will get some angular rotational stuff into the equation as well, then easily ending up at 5 pixels, 7, or even more than that. So there is one very good example that is where we applied the AMC on our Osprey 4.1 in the Vexcel LiDAR program, where we covered London at 3.5 centimeters, because AMC forced us to do that in that range, and that day, honestly speaking, was not the perfect survey day for flying. So we had like values up to 11 pixels, and the Osprey was able to compensate that. Not perfect, so not absolutely perfect, but still easily on a quality level that you can use that data. So really go in, fly, get your data, get everything you want. Basically kind of a one-shot, one-kill opportunity is what you will get with Osprey or Dragon systems. Basically everything that utilizes the adaptive motion compensation. And with the examples,
perfect, great. No, sorry.
With the examples that we have shown today, we just wanted to demonstrate that consistency really matters for your projects, because flying is a dynamic thing.
The coverage of the narrow alley in Graz depends on the flight direction. Did you consider the geometry of the alley during the flight planning? So that's the first question, and I would stop here and answer that, and then I continue as there's a follow-on question. So my feeling is that it's quite independent from the flight direction, because thanks to the LiDAR has always nadir and oblique, or nadir and side view across the track, because the beam goes left and right. So that is automatically coming with the concept of the LiDAR scanning the flying line across, and with the new scanner of the Dragon, it has also nadir and tilted views along the flight line. So the combination of both always ensures, even if the alley is at any angle to the flight line, that you have true nadir as well as tilted views and scans and measurements on the facades. So that would be my approach to it. But I'm looking on Bernhard. Bernhard, do you want to give any color to that? What's your thinking about that?
Yeah. I mean, the geometry of the object, it depends somehow on the measurement rays that reach that object for the kind of coverage, for the measurement points that you get. The example that we have seen, that is at a slight angle compared to the flight direction. So flight lines were in north-south direction, and that alley is going from the southwest to the northeast. So that might impact, of course, the collection in this particular scenario. But in a city center, there can be alleys, streets, roads, buildings in any direction. So this is one example for where the coverage works very well. I mean, alleys in any other direction, they are captured in a very similar way. So this is not just one unique example that we have been showing. This is like a typical example for the performance.
Yeah, great. Perfect. Thank you, Bernhard. Another question: what are the advantages of Dragon compared to the dual hedge installation of the RIEGL camera series with the RIEGL VQ 1560 laser series, apart from the costs? So in our understanding, a dual hedge installation with two high-end sensors installed, like an RIEGL and a 1560 or an Osprey and a 1560, provides better flying efficiency and more versatile mission parameters compared to the Dragon. So an integrated system means squeezing two technologies into one housing to save space so that you can fly with one hedge and to save a little bit of costs. So the integration comes for some disadvantages compared to two individual high-end premium sensors like an Eagle and Osprey together with a 1560 laser. These high-end installation, this premium installation will always get you more versatile mission parameters, better flying efficiency, and a fantastic data set. So the reason why putting everything into one housing, why integrating the two sensors into one housing is that not a lot of people have dual hedge planes, and it's a reason of costs. And that comes with a bit of disadvantage in the flying efficiency and possible mission parameters. So the Dragon is the best-in-class hybrid sensor system, but when you have a dual hedge and you fly two premium sensors, you can go beyond what the Dragon does for you. Marc, Bernhard, fair statement?
Yeah, absolutely.
Great. Thank you. Thank you. Question: which version of the camera operating software course is required to operate a UCO 4.1 in nadir only mode?
That is camera operating software version 8. So version 8 was the first one which is supporting this mode, and since then it's supported. And it does also require UltraMap version 6.4 a minimum.
Okay, where can the COS version be obtained, Bernhard? Is that for download for our customers?
Yeah. So just reaching out to our support team, and they will provide, or just have a look on the FTP in the download section.
Perfect. Great. Okay. Next question: is the workflow for the image data in UltraMap the same as for the other UltraCams?
Yes. The workflow for the image data from the Dragon is exactly the same as for our other cameras. So for all UltraCams, it's identical, and there is no additional training effort needed for working with the data. The only step that is new for the Dragon is, if needed, then you can extract some features to be used as tie objects and then use these in the LiDAR processing to make sure all is well aligned. But besides that, no changes at all.
Perfect. Thank you. So next question: can you please comment on the possibility to perform a hybrid bundle adjustment for photo and LiDAR data simultaneously and together adjusted? Is it worse or the two? Is it worse or the two pipelines, image and LiDAR, will stay separated as georeferencing is good enough to merge the data?
Mm-hmm.
So, that's a question for you. Yeah, please.
Fair question. So we have been experimenting quite a lot now in this field, and for a number of use cases, it's perfectly fine to use the two workflows as presented, using UltraMap for images, using RiPROCESS for the LiDAR data, using tie objects, a handful of these, make sure the data is well aligned, and then deriving products like the mesh and so on. However, there is no limitation to stick only to that workflow. So indeed, for highest possible accuracy, why not? Why not do a hybrid bundle adjustment? So the data formats, interfaces, they fully support that. So there's the full flexibility available.
Perfect. Bernhard, there is a question in the chat which is which go with that. And the question is there a possibility to automatically derive ground control areas for LiDAR georeferencing from the nadir or oblique imagery?
Yeah. So in our workflow right now, there is no such possibility, no such tool to automatically derive such planes. But yeah, as we have been discussing earlier, the approach is to allow easy manual extraction of such features to be used. Manual for the reason of being sure all the quality of the measurements is very high. The number of the features does not need to be very high because it's just for aligning the two blocks of data well to each other. So therefore, it works quite well in that approach, and it's not a huge, significant manual labor effort in the workflow overall. But on the other hand, if there is a need or a requirement for using more TIE objects, then using third-party software, that can be done. So our workflow is like focusing on the high throughput, large amounts of data, and being done that in a high quality way. But for some shifted requirement, then for sure that can be done. So we have prepared a number of workflows and tools, so being able to respond to various needs. So if there's a specific requirement to do it that way, I'm happy to talk about that in more detail in a call.
Perfect. Thank you. So next question here is, why is it necessary to align the LiDAR data with the photogrammetric data during post-processing? Isn't that done once as part of the sensor calibration? Bernhard, more details on you, please. That was just said, of course, we calibrate the two subsystems together, but there are impacts from the real world, and there's a difference between relative and absolute accuracy, and that's why this is part of the post-processing workflow. But Bernhard, please give some more color to it.
Yeah, fully agree. So the single components of the system are being calibrated. The system itself, the combination of all the components is calibrated. And we do the flight with one platform and using one trajectory. But there are some influences, of course, impacting various components in different way. And for imagery, there's usually the workflow using ground control points. If LiDAR is just relying on the trajectory, then there might be a need to adjust that to get the best possible fit. So therefore, we are discussing this workflow. However, this is not a mandatory workflow. This is optional steps. So if the let's say direct georeferencing for LiDAR, so being based on trajectory and strip adjustment, is good for the project, it's perfectly fine.
Maybe to dive a little bit deeper onto that question, just from the calibration side itself. Whenever you are calibrating something, it's always a snapshot of its thermal state at the moment when you do the calibration. So even within the single component, let's say like a camera here as an example, it's a snapshot of that thermal setup. So if you're using it in a different thermal setup, then you either need to somehow deal with that or compensate it in post. And therefore, if you do the highest quality calibration, as we do obviously for both of the parts and for the system, still your application when you are using the product will be in a different environment. And therefore, it's sometimes necessary to calculate these tiny remaining differences. So we are not talking about any large differences, as Bernhard was stating.
Perfect. Thank you, guys. So very nice comment. Congratulations. Dragon hybrid system is very expected on the market. Thanks a lot for that very nice feedback. Next question here is, does the LiDAR always capture all 5 angles? The answer here would be yes. The LiDAR is always collecting the tilted beams and also the nadir part. Next question. We expect that the flight and LiDAR parameters need to be very carefully chosen to make sure that the point density is as uniform as possible. Are there already some recommendations for given image ground sample distances? So in general, I would totally agree. The LiDAR, well, the benefit of big benefit of the LiDAR technology of the Dragon is that it can be configured in a way that the across and along track point spacing is very, very similar. That's one unique point of the scanning mechanism with the rotating polygon, that we have that the system can be configured in a way that the along and the across track point density is very, very similar, and that is different from lasers who are using rotating or this oscillating or the ellipsoid scanning mechanism. They have a very non-homogeneous point density across and along the track. So the answer is yes, that it can be configured in that way. And the next part of your questions, are there already some recommendations for given image ground sample distances? Here, I would say the point density, the points per square meter and the DST should fit together to make it work together. Bernhard, can you give some more color on it? What we usually think, what ground sample distance should have, which point density and so on. Do we have parameters for that?
Mm-hmm. Yeah. I mean, there are some numbers that can be calculated. So depending on the flight parameters, there can be numbers for the point density, also point distribution be derived. But it's not only that, it's also the overall project configuration, which needs to be fully considered because of the sideward overlap, which is also very important, which also contributes to the distribution of the points. And as we have been discussing during the presentation, for a single flight line, there can be, as in our example there, 25 points or 26 points per square meter. Adding sideward overlap, like typical image sideward overlap of about 60%, that adds up then to a total number of up to 100 points per square meter. So yeah, considering all of that, we can give some kind of prediction for how the points will be distributed, but it depends on so many variables that I would say it's not very easy to give just some general guidelines for that, but rather on a case-by-case basis, try to find the optimal.
What we can maybe add to that is that it's always a balance between the point density and how uniform your LiDAR scan pattern is going to be. So we can come up with something that's nearly close to being perfectly uniform, but that would sacrifice the point density a little bit. So it's always balancing the two against each other to get the best data quality or the best data for your specific project needs.
All right, next question. What is the absolute accuracy can be achieved without using ground control points?
So for LiDAR, we have been checking a few data sets, and the positional accuracy is typically well within the GSD of the images of the nadir image. But of course, using not any ground control for LiDAR, it then depends on the trajectory. So that needs to be of high quality. So also here, not that easy, I would say, to give just one single number that is valid for all, but it depends.
Good. Remark, there can be beat frequency effects due to the different viewing angles of the scanner. That means that the scan line separation varies in a single flight line. This effect should be minimized by planning. I can't exactly comment on that. Marc, Bernhard, Is that something?
So for if this is going to basically in the how lines and how this all interacts, you would get so the RIEGL RiParameter software would give you a quite good idea of how the points basically are mapped on the ground. So if you want to get an idea that you will not get any unwanted effects, this is you are able to see and to deal with that in the setting in preparing your project. So as you rightfully stated, this can be checked prior to flying the project and then optimized for best quality or for best uniformity, I should say.
Perfect. Thank you. Okay, so there's another question. Do you also plan a hybrid RIEGL LiDAR system for large areas? Well, never say never. So we'll see what the future brings. But we just started with hybrid system, so we can expect that there's more to come. Yeah. So again, thanks for joining. Also, thank you very much for Bernhard, Marc, and team, the marketing team contributing to this webinar and doing an excellent job. So thanks to everybody, and looking forward to seeing you in person soon.